Good evening, y'all. It would help if I put my mic on, wouldn't it? I remembered everything else. Hey, I'll bet that sounds better, huh? Check the meters there. Well, good. I was feeling like really prepared and really with it and really excited. So I'm glad I had a little hiccup here at the beginning just to get a little of those yayas out before we start. Welcome back for another Sunday night to an Electronics Bash Fundamentals of Electronics and Programming stream. I'm Jeff, your guy in the chair. As always, we're gonna wait a few minutes for stragglers to roll in before we talk about tonight's topic, which is object-oriented programming. And if you can't tell, I'm a little what the kids call hype for this evening. Because I think this is going to be a really fun topic to talk about. And one of the reasons I'm most excited is I know over the course of talking with people about this stream and the episodes and the topics, like, I know there's people who are engaging with this on all different sort of like levels of intensity, like from following along and writing the code as we go and trying it out live and really testing all these skills, and then the other end of just like sort of just absorbing general knowledge, to like, oh, that's an interesting thing, to like somewhere in the middle where it's like, okay, I'm gonna make a note of that concept, but it's not worth my brain space right now to remember all the like the practical implementation details. And just to be clear, none of that is wrong, right? I do a lot of my own YouTube learning at every point along that spectrum, where it's like, I need to know how the requests library works in really specific detail, like why is it breaking in this way, or like, hey, is there a way to like build a graphical user interface? Oh, there is. Oh, that's kind of cool. I'll watch that for a little bit. Anywhere in between. The point is, tonight's discussion, I hope, will be useful to you wherever you are on that spectrum, because object-oriented programming not only is a pretty fundamental concept in programming in Python, but it translates to many, if not all, contemporary programming languages, right? So if you end up writing code in C++ or Ruby or JavaScript or Java or any of these modern languages, or really any, most languages in the last 20 years, let's say most, not all, have some kind of object-oriented bent to them. And so tonight, even if you're like, not going to memorize the object-oriented syntax tonight, I hope you'll take these concepts with you as you go off and do other fun things. I think the only other thing to mention before we get started, tonight I am drinking, as always, it's like blown out by the camera. You can kind of see it there. I'm drinking a GD Pigeon Porter from Spiteful Brewing Company here in Chicago, given to me as a birthday present by a friend, so thank you, Martha. It's really good. It's like the first week I'm drinking a dark beer as we're getting into colder weather here in Chicago. It's intense. There's a reason I guess I've been drinking IPAs this whole time, because they're light and refreshing. You can carry on. This is a serious beer. I mean, it's 8.2%, and dark and nutty. And I think we'll have a good time. I mean, I know I will. If you're drinking something interesting out there, let me know. If it's just water, I mean, I hope you're hydrating. I deliberately have a lot more hydration fluid standing by this week, because I know I get a little parched as we get into these drier months, so. All right, with that, with a nutty ale and a sip of water, I think we are ready to dive into tonight's topic, object-oriented programming. Let's do the thing. There we go. Ooh, and now I'm over here, and it's all very good. I got the number right, number 25. It's object-oriented programming. I got the date right. We're doing great so far. So things we're going to talk about today. We're going to talk about classes in Python, which are a sort of the core structure of an object-oriented approach, using existing classes and building our own, how we would use that structure to organize behavior, and then we're going to fold some of that knowledge into the PyGame program that we started building at the end of last week's class. Cool? So, things we're going to make use of today, we're going to make use of the PyGame library that we used last time, also the random library, and a couple of others. All of the ones that we'll be using this week should be pre-downloaded in the Thonny IDE if you're playing along in Thonny, whether you're on a Raspberry Pi or on your PC or whatever. Thonny's available, I think, for Mac as well. So you should have all these downloaded. If not, you can go into the package manager in Thonny and download the latest version. So, PyGame, great little library. We'll be using it at the end of class today. I put the documentation link in here because PyGame is a pretty convoluted library, so if you are following along at home, having that library open is maybe not a bad idea. I should also say, for those anyone who happens to be new, hey Nate, no Nate, your timing is great. We're just diving into like the meat of the evening and like what we're going to talk about. As always, if anyone out there doesn't know, all of the code and the slides for this evening are linked on my website, jeff.glass/. Just before this started, on the Electronics Bash page, the header says that this week is also internet, Raspberry Pi and the internet, but the link and the slides and the YouTube link and all that is correct. So apologies, I'll fix the website later. It didn't feel like high priority. You guys know where to find it by now. So let's talk about classes and object-oriented programming. And I think the way that we're going to start this is actually by looking at a little bit of code. We're looking at a little bit of code when it loads. How odd. Excellent. Hi, Chris. Nice to see you. Well, Chris, y'all might be more on time than you think. It seems like the capture card that does my Raspberry Pi is not necessarily loading. Why would that be? Raspberry Pi off on. We'll do a little quick configuration here. We'll deactivate, activate. What's going on there? This was working just 10 minutes ago when my wife and I did our test. Well, I'll tell you what here. Let me, if I put you here, I think I can still talk to y'all, but you don't have to look at my, I'll describe to you in audiobook fashion what's happening. Getting access to the part where the HDMI extender plugs in requires a pretty awkward lean across my setup, and you'd be looking at my butt. And since I don't want to be demonetized, I feel like we're just gonna, gonna leave you on this no-see screen. Let's come back to this. Ooh, there we go. Yay, there we go. Now, if my monitor would come back so I could see what I was doing, we'd be all good. All right, one more sec. Let me get that monitor back up. Let me unplug and replug the monitor here. A little backstory for you nerds out there. So I'm using an HDMI splitter so I can have my Raspberry Pi display go into my capture card and also go to a local monitor. And I can't quite figure out from what's going on here which source it's taking the HDCP signals from, which is how the computer and the display communicate to each other what resolutions and what frame rates and things they can variously support. And it seems like now my computer is happy, but my monitor is not. But that's okay. I actually have a second backup monitor. It just means that for the Raspberry Pi portions of this evening, I'm going to be looking off to a strange place. Actually, we can fix that. We can fix that too. Stand by, please. Because my webcam is on a 3D printed mount that clips onto the front of my shelving here. So if I move it, and again, I've turned you off because this would be kind of a dizzying experience to do live. But if assuming there's not too much flare, and we'll get this other camera out of the way. So this is basically Electronics Bash, the audiobook version. Sorry, Palmer, I know. I do a test of this every single week because this is the weak link. And now it seems like it's all failed me. Well, there we go. So I can kind of look at y'all now, and I have this backup monitor. And we'll roll with this for tonight. And we'll pretend nothing happened. We'll cut this all out in post. It's fine. Sorry, Palmer. Where were we? Oh, right. Speaking of streams that don't have class, let's talk about classes in Python. Here, let me adjust this a little bit so we don't have too much flare on that camera, because that's going to bother me, if not you. There we go. All right, you stay there. Great. Hello. Chris came for the screw-ups. Well, Chris, you're in luck. Oh my goodness. It's fun. I enjoy being myself on these streams, and that includes all the goof 'em ups as well. So, to get into the meat of the thing, here is a little piece of code that we're going to start with tonight. This may look familiar. This is some of the code that we wrote 2 or 3 sessions ago to blink an LED on the Raspberry Pi, or really at this point, just to turn the red LED on. And this was some code that I just sort of threw out. I was like, hey, this is how you do this thing. Here is how the code works. Run it, and it will work for you. But tonight, I want to deconstruct a few of these steps that I've kind of been a little hand-wavy over, and what exactly is happening in code like this. And we'll get to more, involved demos of this in a little bit as well. But I really want to make clear, what's happening. Why does this structure with the parentheses mean create a new LED on digital pin 20? Why does this structure turn on the LED? Why is this the format for it? So that's what we're going to get into this evening. I should say, so this example is the minimum LED example on the Electronics Bash site. There's an annotated version, which is the same code with comments in it. If you're referring back to this later and you're like, wait, which line does what? Look at the annotated version. But for now, we'll build on the simple version. I'm going to clear some of the shenanigans I was doing down here in the terminal earlier. So this is a 3-line program. It's very simple, and if we run it, and I haven't broken anything in the ensuing weeks, yes, here we go. You can see if I put the camera back on the breadboard there, you can see the red LED turned on. If I come back to the Raspberry Pi, here, I'll do a little split screen there, run code with LED off in it. If I run that, the LED turns off, right? So it still works, still working fine. There's 3 lines of code here, and I want to talk you through each of them and use them to explain what classes and objects are in Python. So this first line here, from GPIO0 import LED. And we've talked about before, the import statement is how we basically bring chunks of code from other files into our own code so we can use them. So in this case, we're saying, hey, someone out there has written a module, a chunk of code called GPIO0. In this case, it's an IO library for the Raspberry Pi specifically. Great. And from it, we want to bring in or import just the LED class. There might be multiple classes in this file, but I want to use just this one. And I know we haven't done a formal definition of class yet, but it's the first line, it's the first explanation. This line really is the meat of the thing. So much like we would with any other variable, you know, if we were to say, my name equals, quotes, Jeff, right? We know how that looks as a variable assignment. We have a new variable that we're calling by the signifier, the title, the name, my name, and its value is going to be the string of Jeff, right? We're doing the same thing here with this variable name red LED. That's going to be its name, its signifier, its variable identifier, just, you know, a human readable version of something. And this syntax here, where I say LED and 20, is how I'm going to construct a new instance of the class that is an LED. If we had a class of chairs, and again, I know we haven't formally defined a class yet, but we're going to build some intuition around it first, right? If I had a chair class, I could say, you know, my chair equals, say, chair. Maybe it takes parameters called for the number of legs, and the color is brown. And by writing in this syntax, I would create a new chair object and give it any parameters that I need to give it at the time of creation, right? The LED class itself, by the way it's written, doesn't let me create a new LED object without telling the code what pin it's attached to. I can't sort of create a generic unattached LED. At least I don't think I can. Yeah, it says no pin given. GPIO pin missing, not great. Right, it says I insist if you're going to create a new notion of an LED object, you tell it what pin to be attached to. Right? Once we have what's called an instance of this class, an instance is being a single variable, basically one object we can play with, then we can run functions that are specific to that object. Right? The same way that we would use a function like print, or a function let's use some functions we would use with print, like string function, str of 3. I can now, once I've defined an object, I can run functions specific to that object. I can command not the general program to print something to the screen, but I can command this red LED, which is an LED object that I've named red LED. I can tell it with this function to turn off or on or blink, whatever the functions that I'm using are. When we use functions in this context, the functions of a specific object, we call them methods. So in this case, this red LED object, which again is of type LED, it's an LED object that I'm calling red LED. Any LED object will have an off method that I can use. And methods, just like classes, when we instantiate an object, might take some parameters. We've seen this all before, right? In the same way that we might say, you know, red LED dot blink on time equals 1, off time equals 0.5. Right? We can give our methods of this object some parameters when we call them to change the behavior of that object, right? So that is the core of what a class and object is, but let's make that just a little bit more formal. I know that was a little bit casual, so let's explain it in a little bit more detail here. Let me make sure we're focused here. So, right, we've been used to thinking about, you know, sort of data that we have floating around in the world, whether that's strings, numbers of various types. We looked at lists and dictionaries recently, you know, various ways of storing information about what's going on in our code or what's going on in the world. And we also learned how to define our own functions 2 sessions ago, last session. It all blends together. Using this syntax here, though, we can define our own functions to do things for us in our code. We use this def keyword, the define keyword, to define a function. Then we can Also give it some arguments if we want to. We can do whatever we want inside the body of the code, and if we need this function to hand back some information into the code from wherever it came from, we can use this return keyword to send the value we've calculated, say, or the result, back to where the function came from. We don't have to include arguments in our code, much like the on and off for the LED example. Sometimes you don't need to tell the function to do anything more than just run. You also don't necessarily have to return anything. Your code could just go out and do something, and that's it. No side effects, as they're called, and that's fine as well. So let's take a little quick look at that in code here. Let's just start a new file. Just so we're clear on the function syntax before we dive right back into classes, right? I could say define a function called square it. It's going to take one argument, which is going to be a number. I need a colon after it, right? That's how Python knows I'm going to start a new block of a definition. And I'm going to say, I can just do this all in line. I can say return num double asterisk 2, and you recall this syntax in Python is your exponentiation function, right? So now I could say a variable x equals 1, print x, and print square it of x, right? And if I run that, oops, can make me save it. This is going to be my square demo. And I run that, and I get the square of 1 is 1. Like, that's not a very interesting example. Let's do x equals 5. I'll print 5 and 25. And we can do it for a range as well. You remember our for loops from a couple sessions ago? For let's do for x in range 10. So remember, that's going to give us a list of numbers from 0 by default up to 1 less than 10. So range from 0 to 9 of 10 total numbers. For that, I'm going to print x, and I'm going to print the square it function of x. And I need a colon there. We'll run that code, and you'll see I get a list of the numbers from 0 to 10 and their squares. Palmer says you're getting all of these parameters from that specific library correct. Yes, like LED20 only works because I know that the LED object needs a number. So things are dependent on which libraries you list at the beginning of the code. Yes, very much so. Yeah, so in something like our LED code here, right, you would know by either looking at the library reference or the library code or its documentation that the LED object requires this number. In fact, let me show you real quick what that might look like in the documentation. Just because, as you know by now, I'm a big fan of reading the documentation. Let's look at the GPIO0. You guys have GPIO0 documentation in my my quick access now. I will go to output devices. I'll go down to, let's see, regular classes, LED. And it says the GPIO0 class, GPIO0.LED. Put this in your back pocket for about 45 minutes from now. Extends digital output device. We'll get to what that means in a little bit. But you can see here that this LED object needs some parameters to instantiate it. Yes, Palmer, I read up on GPIO0 and specifically this LED object before I could use it, right? And this is telling me that it needs, in fact, so it says up here in the function definition what it needs, but this documentation is actually particularly nice. It tells you in more detail what each of those parameters are. Because I need a pin that's going to be connected to. I could go to this link if I needed more details on how it works, because maybe it's not entirely obvious. Is it active high? Do I want to give it an initial value? And so on. And I can tell by this function definition that active high, initial value, and pin factory, which has to do with how the Raspberry Pi is handling the digital output, because these have values, assigned to them, it looks like in this class definition, those are going to serve as default values for any of those parameters. And it means I don't necessarily have to give them to my constructor, my function that actually creates the object, when I use it, right? But this pin value, where the LED is actually attached, since it does not have a default value, that's one way that I know I'm going to need to supply it. I could supply any or all of these other three values if I wanted to or needed to, but because pin doesn't have a default, I'm going to have to provide that value when I create an LED object, or I'm going to have an error be thrown. But yes, Palmer, it's all about reading the documentation for sure. So let's see here. So if we were, where were we? Oh, we were defining functions. We were just doing a quick review of how you define a function in Python, right? With this def keyword, and using the, using the return keyword to send some data back where it came from. And does this sort of make sense what the return function is doing? Basically, when I'm nesting function statements like this line here, for example, print, and then within the print statement, square it, and then within that x. In order for the program to run this print statement and do what it wants to do, it's going to say, okay, I'm getting ready to print something, but I don't know what to print until I solve, whatever this other function is. All right, well, let's run that function, and I'll give it whatever parameters that my programmer has told me to. And once I've run it, it's going to give me some value back, and that will basically take the place of where this function is, and that will be returned to, that will be the result that is fed into the print statement, right? That was, again, a kind of a hand-wavy explanation. But in the same way, right, there's no reason I have to just feed a number in here. I could feed another function in. I could say square it twice. And now we should get the first 10 numbers and their squared squares. So 2 to 16, 3 to 81, 4 to 256, and so on. Right, we can sort of nest these functions as deep as we want to go. So that is the syntax for declaring a function. And I brought it back because I think it's relatively easy to parse, at least if you've seen it a little bit before. Let's look at the syntax for declaring a new class. Let me come you back over here and bring up this. So we looked at data, we looked at functions. Classes really are just a group of related data and functions put together. You often hear this referred to in programming classes as encapsulation, the idea of taking some of our data and some of the functions on that data and putting them into one idea together. So here's a really simple example that I wrote while thinking about the little the jumping around guy program that we wrote at the end of last week to show off the syntax of how you define a new class in Python. So, much like we have the def keyword for defining new functions, we have the class keyword for defining new classes. Much like a function definition, we have the name of the class that we intend to use, and then we can put things in these parentheses here. Again, put a pin in that for about 38 minutes from now, and we'll talk about that in a little bit. Within that class, we have a very special function we can use called init. And it's actually __init__. You'll see this quite a bit as we go forward and in Python classes. These methods that have two underscores before and after is how in Python we denote special functions that are used in very specific circumstances, functions that mean something special to the Python programming language. The init one is the function that runs when we use when we create a new object of a type of a class. So to go back to our Raspberry Pi code for a second, come back to our LED example. When I am assigning the variable redLED equals LED20 using the name of that class, what's actually happening here is that the __init___ method of the LED class that someone else wrote is running, and that function is being given the parameters that I give it, in this case, 20, right? So if we're going to write our own class, we need to define what happens when we have this construction here. So in the LED class's case, presumably when I say redLED equals LED20, it's got to do quite a bit of work to set up that object. It's got to figure out, am I really on a Raspberry Pi? Are there 20 LED, digital output pins to use? Is pin number 20 already taken up by some other function? Okay, if not, attach, lock down that pin so no one else can use it. So this function can be doing quite a lot. But for our purposes, behind the scenes, we don't really care what it does as long as we get a reference to this object when we come back to it. And I can think of this as an LED object. And that's what the init method will do for us. I should say one term of art that shows up in these cases is rather than saying double __init__, which is a bit of a mouthful, even for me who could use a beer break at some point, you'll often hear these referred to as either special methods or as Dunder methods, Dunder being short for double underscore. So this is the init Dunder method. I'm honestly just going to refer to it as the init method for the rest of the time, because you rarely see init, as a function you might write yourself. But just know that you want to precede it by these two underscores and follow it with these two underscores, because that is the name that Python knows to call when you use this function, when you create a new object using the syntax that we saw with the LED. Right? So just like our LED class, in my hypothetical treasure class, All of my treasure objects are going to have a name, and I'm going to make the user supply one. I haven't given it a default value here. I'm going to have the treasure have a default value of 1. 1 what? I don't know. It's going to be program specific. But let's say they have a default value here. So the user can supply a new value, but they don't have to. Then within that class, and we'll do this as an interactive example in a second here, inside this method, this init method, I want to basically have this specific treasure object that I'm creating, have it have its own name and its own value. I don't want every single treasure object to have the same name and the same value. I want each specific object to have its own. And that's what this self.name, self.value construction does. And we'll look at this in detail in a second here. In fact, in a second can be right now. We're on the internet. We have the power. Let's do this. So it's going to take me just a second here. Let me see if I wrote the treasure code in here ahead of time and if it's the same. Yes, here we go. So here's our function, our class, treasure class we were just looking at here. We define our init function. We do self.name and self.value. In fact, let's just ignore that extra code for a second here. We'll just start with a very, very simple class. So to use this class, to start using it, I can instantiate or create a treasure object, just like I did the LEDs. I could say my bar of gold equals treasure. Its name is going to be bar of gold, and its value is going to be 100 of something. I'll create another treasure object. I'll call it my penny. It's also a treasure object called penny, and I'm going to leave it with a default value of 1. Maybe it's in cents in this case, in which case it's a very, very small bar of gold, I suppose. So if I run this code, nothing will happen yet, of course, but I have instantiated these two objects. So now I can do things like print out the values of the various variables. So I could say print my bar of gold dot name. Right? And it will print that its name is bar of gold. So what happened is, when I created this bar of gold as a treasure object, and I fed in bar of gold, the string, and its value parameter of 100, the init function took in those two parameters, and then assigned them to that object's local parameters. It said, okay, well, that object that you gave me, its name, that object you gave me being my bar of gold, that object you gave me, its name is going to be the name that you passed me. And its value is going to be the value that you passed me. Your YouTube thumbnail starting to make sense? Yeah, I thought, with the coins in the treasure box, I thought it was eye-catching, and I didn't know how to represent the abstract concept of a Python class. But here we go. So similarly, right, if I come down here and I print penny.name, and run that, I get bar of gold and penny. So we see that these two objects, though they both are treasure objects, they each have their own individual values for their parameters name and value. We can print those out as well. So let's say print my bar, let's do this in one line. Print name plus string value. We have to do my bar of gold dot value because we want the value parameter specifically of that object. I'll say plus string penny dot value. I don't think this is going to be formatted very well. Yeah, I had no space in there, but that's okay. Bar of gold with its value 100, penny with its value 1. Right? So by using this dot construction, we can reference the attributes of a specific instance of a class. Let me say that again. So the bar of gold is a treasure object. It's a member of the treasure class. Penny is a treasure object. It's a member of the treasure class. They both have their own unique values for their name and their value parameters. And the way that we get them out to do things with them is by using their name, dot, and then the attribute you want to reference, dot name, dot value, and so on. We can also do the same thing to set those values. So let's get rid of this penny, for example. I could say my bar of gold dot name equals let's see, let's call it Jim. We'll change his name to Jim, and then we'll copy and paste this this statement down here that just prints its name and value again. And you'll see that the first time we printed out the name and value of this my bar of gold object, its name was bar of gold, but then we changed that attribute to be Jim, and so now we print out Jim and the value of 100 that my bar of gold has here. So these parameters, these attributes, act just like any of the other variables we've been playing with. They're just associated specifically to these new named objects that we have here. What might make things a little bit simpler, if this is something we're going to need to do a lot, is say print out the name and value of our objects, is we might create individual functions associated to objects of a particular class. And we can do that much like we would for writing our own generic functions in any other case. That's what I commented out up here. I've written my own function which is specifically associated to the treasure class. Again, using our def construction for define a function. I can say, I've defined this function that says get introduction. You'll see though, so get introduction, what it's going to do is return a string that says, hello, I am called name, and I am worth value, right? Not a very interesting function, except it's going to save us some typing of some things down here and give us a little nicer formatting. So I don't really need to pass it any parameters to do anything, you know, functional with. But you'll see I still have given it this one parameter called self. And this is something that you will do anytime you are writing a function that is associated with a specific class. This, the presence of the reason you need a parameter here, let me say, is that this function is going to be run by a particular object, and self is how we sort of identify what that object is. So basically, when I run down here and I say print, instead of doing this manually, I'll say print my bar of gold dot get introduction. Right, when I run it down here, I'm not going to feed it in any parameters down here in this function. I'm just going to have it, it's going to build this string, and it's going to give me this string back. It's all going to be very fine. Here, we'll run that. We can see, hello, I am called bar of gold, and I am worth 100, right? It built this string for me and returned it back. But see down here, I didn't give it any parameters to run with, because there's nothing really to change behavior-wise. But when I defined the function, and this is important, when I defined the function, I used one parameter, and I called it self, which by convention is the parameter we use. And self will represent the object that's using this function anywhere within that function, right? So that's how I reference in here. Self.name is going to refer to the name parameter of the object that called that function. And self.value is going to refer to the value parameter of the object that called that function, right? So again, we can use that function for any of our objects of the type treasure, introduction. If I run that, now I get, hello, I am bar of gold, I am worth 100. Hello, I am penny, I am worth 1, right? Because again, both of those objects have their own unique values for their name and their value, their name and their default value in the penny's case. Yeah? Questions so far? I'm really excited to talk about this. It is a fairly abstract concept, so like, if you have questions, shout them out. And as always, you know, the question break is also a beer break for me. Got porter up my nose there. That's sort of exciting. That's a new one. It smells very much like fall in my face right now, which is kind of exciting. So that is the basics of the syntax of bar of gold equals dollar. Yeah, that's a better construction for sure. That is the basics of the syntax of defining our class. And just to show you, a slightly different graphical form, if that is useful to you. So when we were defining an object that is a type of a class, we use this construction where we give it a name, a variable name. In this case, we would call it an instance name, equals, the class name with the parentheses after it. That's going to be our constructor. It's going to tell us to build a new member of that class. And again, when we use functions that are associated to a specific type of object, we call them methods. We call them the methods of that class or the methods of that object. And these, we can do anything that we want to with these methods that we could do with any other function, right? We could have them modify the values of our attributes. So for example, let's write a new function that takes our treasure, whatever it happens to be, and increases its value by a certain amount of interest. So let's call it apply interest. That's going to take our self parameter. Our function's always going to have our self parameter. And then I'm going to say interest rate. And I think to be kind of my later self, assuming I was going to come build this into a program, I'm going to say interest rate is an integer number, is a positive number of percent, i.e., 5 corresponds to 5%, just so I know like how the math is working out. Should it be 5? Should it be 0.05? Should it be 1.05? or so on. So that'll just be my little note to myself, right? I need a colon after my define statement here, so Python knows I'm defining something new in a block. And I'll say, let's define a new variable. I'll say the new value of my, oh, here, I don't even need to do that. I can say self.value equals value times, and because I want to give this whole positive percentages, I'm going to say 1 plus interest rate divided by 100, right? So if I have 5% interest being applied, what I really want is to multiply by 1.05, oops. And that's what this math is going to take care of here. So all this is going to do is apply a new interest to the object and redefine our internal value to be the original value, which should be self.value times this modifier that we have here. Let me actually show you, this is a very common typo. Let me show you what happens when I try and run some code that uses this apply interest function. Let's get rid of some of this. Let's see, I'm going to print my bar of gold.value. Then we're going to do my bar of gold dot apply interest, and it will apply interest of, I don't know, 10% is going to be great. Let me format this correctly with the self.value here, just to show you what it will do, and then I'm going to break it, and we'll see what happens in this very common mistake. So what we should get is my initial value was 100, and this is interesting. My new value after I applied 10% interest to it was 110.000000001. Palmer asks, when you hit return after that colon, did the program automatically indent the next line for you? It did, actually, yes. That's one of the nice things that Thani and a lot of IDEs do, is if you have a common construction like define a new function, you put a colon, you hit enter, it automatically does a new line. I think it will do the same for like a for loop. Yeah, automatically did that tab in, and so on. Just to help you like keep the indentation matching, especially because Python depends so specifically on indentation. It tries to help you out by adding those indents automatically. So we can see this function essentially did what we thought it would, right? It took in our initial value, it multiplied it by a small number, in this case 1.1, and gave us our new value. What's happening down here, why this is 0.000001 instead of just 110, has to do with the way that computers keep track of fractional and decimal numbers. You basically don't have a way of precisely representing the idea of 1.1 in binary, and so you in floating point numbers, the closest that you can get to 1.1 is probably 1.100000001, and so when you multiply all that out, you get this very small sort of hanging remainder here. Which may or may not be what you want. Like if you were calculating interest on something, you probably want your numbers to sort of be as precise as possible. But what does precise mean in this context? In any case, we'll get into floating point math some other day, but just know this is not an error in my code. This is an error in how, no, this is a feature, let's say, of how computers handle numbers. Curious. Floating point rounding errors would be the thing to Google if you get curious about it. So what did I promise to do? Oh, I was going to break my code to show you what happens, right? So let me break this apply interest function by removing this self. And this is, I mean, you saw me make this typo live, right? I often forget that like this is supposed to be the value attribute of a specific object. I just forget to type the self dot whatever, right? Let me show you the error that results. It says value is not defined. And if you're writing code and you're newer to writing code, this can be a really frustrating error to come across. Like, hey, value is defined. I put value up here. What it's saying is I don't have a general variable called value. All I have is an object or objects that have this value attribute to them. In fact, we could break this even further. If we did define a global variable like value equals 5, right? And I run this code, the code will run. But you'll see, rather than taking the value attribute of an object, it's just treating value like, well, like it would any other variable and slurping that in. And if this was my bar of gold that got devalued to 5.5 units instead of 100, I'd be pretty pissed. So in this case, because I want the value attribute of this specific object, I need to use self.value. Make sense? So we can do a lot of things with functions built into various objects. You can also, let me show you a couple more things you might do and reinforce the idea of these Dunder methods, these double underscore methods. I just like saying Dunder, really. So let me show you what happens if we just so let's create a new object. Let's see, how about one with more sensibility in it? Let's call this a euro equals a treasure with a value of euro, a name of euro, and a value of 10. That's a 10 euro note, let's say. Right, run that code, make sure nothing's broken. Cool, nothing is. What happens if I just try and print out that object? Right? If I just say print, what I get is this kind of goofy syntax that says double main dot treasure object at oxb5e6aad0, right? This is not necessarily a specific address in real memory, but it acts a lot like an address in the computer's memory in that it sort of will be unique for any object. Basically, it's saying, hey, I don't know how to print out a treasure object. You've never told me, so I don't know. It's a treasure object. It's in memory. That's all I know how to tell you, right? If we want to do something a little bit more useful, we can actually define the way that our classes are printed out to the screen using another Dunder method called string, str, which I don't think takes any parameters, but if I'm wrong, we'll see in a second here. And in this case, I can define how my object is printed out. So I could say, let's just return, I'll say treasure object with name plus self.name plus and value plus self, let's do string self.value. Yeah? So now when I run this code, what I should get is now a nice string representation of my object, where it says treasure object with name euro and value 10, which might be significantly more readable than this anonymous treasure object here. This can be really useful if you're using, say, a lot of treasures in your code and something is breaking. You can start putting print statements and printing out your own objects back into the code at various points. So there's a whole variety of these Dunder methods, init and string kind of being the most common. But you can see, so I didn't have to call, say, the treasure.str method anywhere down here. The str method, or the Dunder str method, the Dunder string method, was called automatically when I tried to use this object in a context where a string is expected, like when I tried to print it. That's what makes these double underscore methods special, is you don't call them explicitly all of the time. They're just, functions that the Python core library knows about and says, okay, if the user tries to use this object where I think a string should be, I'm going to call its Dunder str, its string method, and use that. And if it doesn't have one, I'm going to fall back to this very basic, just to get something on the screen method that prints out the name of the class and where it is in memory or so. So lots of things we can do. We can do all kinds of things with these interesting functions. Questions? One thing I've noticed is, the office that I'm in, especially in the winter months, we don't have the AC on, gets a little stuffier over the course of the evening. Let's see. And he says, yeah, Dunder Mifflin. Oh, Nate, it took me so long. Dunder, that is a nerdy joke. That's quite good. I do like that. Oh my gosh. Very cool. Let's talk about one more big topic before we jump into sort of using these ideas in our PyGame code, and that is the idea of inheritance. Actually, before we do that, I want to talk just a little bit more about the idea of classes and their representation of objects. So, when I say we have a class of objects and we have instances of that, just grabbing things that are close to me here. Ooh, hello. That's my face object. So let's say I had a class that was the Silver Sharpie class of objects, right? I might have a Silver Sharpie class. It might take a couple of parameters like nib width and amount of ink that it starts with. And then I would create a first variable of the Silver Sharpie class. And this one might be called, I don't know, Yellow Sharpie, because it's kind of yellowish. It's got a width of 2 millimeters, and it comes with quite a bit of ink. And then I might create another member of the Silver Sharpie class with the same parameters, and another member of the Silver Sharpie class. And then maybe I create a big Silver Sharpie. And all of these are objects of the Silver Sharpie type. Here, I have a better way to show this. Objects of the Silver Sharpie type, but they are all discrete instances of that class with their own tip width and their own amount of ink remaining, and we can modify the variables associated with each instance of that class without affecting the other ones. So a class just represents a type of object, whether it's a literal object like a treasure or a penny or a silver Sharpie, or maybe a more abstract concept. You might have a class that, say, represents the state of connections between your computer and another one. You might have a class that represents the addresses that your students and teachers at your school want their checks mailed to. Well, the teachers want their checks mailed to. That's where the students get their report card, right? So it may not correspond to a physical object, but you might have a class represents some data and some functions that go together. So like in that address book class, you need a way of storing and sorting those addresses, and you need a way of, say, obtaining the relevant information. Maybe you have a function that calculates if any of those destinations are going to need additional postage or something like that. You wrap all of those sort of abstract ideas up into one class. You encapsulate them into one chunk of code, and then we can sort of treat them as objects together, if that sort of makes sense. One powerful thing that we can do with classes that we haven't talked about yet is use a concept called inheritance. And again, please shout me out questions if you got them. I think I've said before in doing these electronics bash classes, this is one of those times where if I was teaching this class in person, I would be like looking everyone in the eye and like trying to gauge whether people were following along or really understanding. And of course on the internet, that's hard to do. So I'm trusting you out there to ask questions if you have them. Inheritance is the idea that if a class represents, say, an object, a subclass represents a subtype of that object. So, a concrete example, maybe we have a drink class, and that drink class has and represents a drink that you might serve to somebody in a restaurant for writing some code to manage a restaurant's operations. The drink has let's say a size and a name, right? Pepsi, Coke, water, what have you. But within that, we might have a subcategory of objects that represents a more refined version of that class, like a soda pop class. And the soda pop class might need some additional data associated to it because it has some specific properties. Perhaps when we're dealing with soda pop data, we need to know the sell-by date because the soda is going to go flat after a certain amount of time, whereas things like the water and the lemonade, let's say, have no expiration date, right? So a soda pop is a subclass of drink. Palmer says in my example with gold and penny there were no subclasses. Correct. Yeah, so in this example we've been playing with, these are just a handful of objects that are all of the type treasure. But let me show you how you would build a subclass out of this. Let's say, let's create a new object that is, so if treasure is the broad category of objects, let's say, which is a little specific, I know. Sidebar, a lot of these examples that you find on the internet, I sort of troll the web for like, what are the structures like people like to use? Doing like, payroll or like student addresses are kind of the common ones, but I think these will be more fun in any case. Let's create a subclass of treasure, and let's make it iron bars. So lean into like the pirate idea of things, that our wealth is stored in lumps of iron. But the problem with iron is that it rusts, and so it's going to have some parameters and some methods, some attributes and some methods that are unique to this type of treasure. So here's how we would build a subclass of the treasure class called iron bar. Just like above, we'll use the class keyword because subclasses are going to be whole classes in and of themselves. I'll say class iron bar, and man, a lot of digressions here. You'll notice I'm capitalizing treasure and iron bar. That's a pretty common convention for class names, to just show the programmer that they are a class. By convention, variables are lowercase, class names are uppercase. Any case, just so you know. So I'm going to create this iron bar class, and in contrast to what we did above, where I had empty parentheses here. Oops. Oh gosh. Oh no. Clear. Show plotter. There we go. Where I had empty parentheses here up at that treasure class, and I told you that in like 45 minutes you could expect an answer. Well, we're early. We're way ahead of time tonight. It's great. Down here in my iron bar classes parentheses, I'm going to say treasure. And that's going to signify that the iron bar class is a subclass of the treasure class. Or you might also hear this referred to as the iron bar class extends the treasure class. And that nomenclature extends is actually pretty evocative and accurate, because what this is saying is the iron bar should have all of the properties of any generic treasure and whatever I say below. So, for example, let's say I'm adding no additional details to start with. We'll use this pass statement, which you'll recall does nothing, right? It's just a placeholder. It says, hey, I know I need a text here for formatting's sake. Do nothing at all. Well, now I can use this iron bar class. I can create an iron bar object, and it will have all of the properties that a treasure object would have. So, let's say my ingot is going to be an iron bar object. And just like a treasure object, I'm going to need to give it a name. So I will say its name is going to be ingot of iron, right? And now I will, I can use any of the methods I defined for the treasure object. I can say print ingot.get introduction. Takes no parameters. When I run that, you'll see, hello, I am called ingot of iron and I am worth 1, right? And even though we didn't define any attributes or methods for the iron bar class specifically, it has inherited all of the attributes and methods from the class that it is extending. Sometimes we call this the superclass of our subclass. So if iron bar is a subclass of treasure, treasure is the superclass of iron bar in this case, right? So even though I'm literally doing nothing to distinguish iron bar in this case, I still have access to the name, the value, our string function that we wrote, our get introduction function. I can apply interest if I want. Here I can say ingot.apply interest. Let's apply 100% interest before we print things out. We'll see we now have a value of 2, right? 100% interest on its value of 1, right? And this really is the power of subclasses is, you know, let's say I wanted this iron bar treasure that is going to have this rusting property that we'll define in a second here. It would be pretty silly to, you know, take all of these functions that we've written already for generic treasure and rewrite them or copy and paste them down here. By making this subclass, you know, a member of treasure, a subclass of treasure, we get all of this functionality already for free. Palmer says I have a super class on YouTube every other Sunday. Palmer, you're very sweet, and that's a very good pun. I still think Dunder Mifflin might be our top one of the evening. That's really, really quite good. But thank you all for bringing your pun A game to this early fall. I really appreciate it. So now that we've defined a subclass of our treasure object, we can start adding some additional functionality to it, like new functions. I can say define a function called rust. It's going to take our self parameter, just like any other method of an object. And when we call the rust function, what we're going to do is going to say self.value equals self.value divided by 2. Let's say whenever things rust, go through a rusting period, maybe we call this function whenever it rains, its value gets cut in half because a bunch of it rusts away, right? So now if we come down here to our iron bar object, and let's say it's ingot of iron, let's give it a value of 1,000 just to give us something to play with. And I can say, you know, get introduction, right? I'm an iron ingot and I'm worth 1,000. If in the middle here I say ingot.rust, right? I use the ingot method of this object. Now when I introduce, I should see, yeah, we're only worth 500 now. I could call that multiple times even. I could say ingot.rust twice, and now I have a value of 250 when I start here. So you'll notice that this rust method is unique to the iron bar class and not to generic treasure. So if I create an object of just a treasure type, like let's say again, our coin is just a generic treasure, coin with the face of the queen, let's say, and it has a value of 50 to start with, right? If I print coin.get introduction, right, both should work. So I have an iron of ingot that we rusted twice, and we have our coin with the face of the queen. But you'll see, of course, if I try to call coin.rust, I should get an error. It says treasure object has no attribute rust. And that's because this rust function, of course, is unique to this iron bar subclass. The treasure objects don't know anything about it, but our iron bar objects, our ingot object in this case, does have a rust function, so it's happy to run that for us. So really, the gist of the idea of subclassing is if you have a broad category of objects and you continue to get sort of more specific in behavior and attributes, you can define behaviors that are globally applicable or applicable to a broad class of things, and then sort of drill down into more specific functionality or attributes in subclasses of them. This is especially good if you're, defining some object that has a fairly complicated system of working, like objects moving around a screen, sorry, I had a little brain fart there. Maybe it's time for a beer break. I'm sure the beer will help. Let's say you were writing a library to communicate over the internet, right? You did a lot of legwork with how the connection should work and what the parameters are, and then you wanted to create a class that communicates over the internet and maybe sends the same information straight to a file, right? Little tiny change. It would be silly to duplicate all of that effort, copy and paste, have two separate files you'd have to maintain. What you'd probably do in that case is just create a very small subclass of your files from the internet class, say, and just add that little bit of functionality and that does this additional thing that you want it to do. Something you might also do in that case is override one of the original functions. I'm going to show you this example, and I think then it'll probably be time to get into our gameplay example. So our subclasses here, in addition to defining new attributes and methods for our object, they can also override the methods of the original class if they need to. So for example, down here, if within the iron bar class, I say def get introduction, and I can say for iron bars specifically, just going to copy and paste this as a place to start. Define introduction for an iron bar is going to say, good day, because iron bars in our fictional pirate universe, the storytelling here, I admit, has gone somewhat off the rails. Say, good day, my name is something, and I am worth my value, right? So down here, if I have my iron bar being instantiated and introducing itself, and then our coin being instantiated and introducing itself, we will see, okay, this is another good error to observe. You're welcome for making mistakes. Get introduction takes 0 positional arguments, but 1 was given in line 26 of my code. So that's line 26 is this line here when I try to call init.getIntroduction. And what's happening there is, of course, I forgot to put the self keyword in this method of my object. So getIntroduction takes 0 positional arguments, but 1 was given is basically saying, hey, anytime you write a function within a class, I'm going to assume that you have a reference to a specific object there. I'm going to give it to it. And so if you leave that blank, I don't know what to do with the name of that object. So that's why we choose to put self in here. And now if we run that code, we can see the ingot object, the iron bar object, when we call getIntroduction on it, is using the getIntroduction method from iron bar. The subclass's methods will always override the superclass's methods. Or in other words, the more specific definition of that function will always override the less specific definition, which is usually what we would want. Down here, the coin is just a treasure object, and so it is only using the treasures version of getIntroduction. What's really happening underneath the hood here, right, is when we call a function of the iron bar object, it has a number of places that it can look for that function's code to exist. So, take ingot.getIntroduction is going to first see if the iron bar class has a function like that, and it does. But if it didn't, it would go to its superclass and say, okay, does the treasure class have a function like that? And if not, it's going to fall all the way back to sort of some generic functions like str or init or things like that. It's going to say, okay, well, I might just print you out the name and the address where this code is in memory. Fall back to the very, very beginning of things. Code like this is useful in cases, you can imagine if we were building out our game with a bunch of different, where'd you go? Treasure. If we were building out a bunch of different types of treasure, which all had, they all had value and names and maybe some other data associated with them, maybe they have a description for our inventory system and was also generic, and then we needed to define some very specific types like iron bar, pile of gold coins, which can, be swept away by a river over time, treasure like a giant piece of redwood, which you can't carry on your back, whatever you want to do. Most of the time, what you'll be doing is extending your class definitions with new functionality, but especially if you only have 1 or 2 cases where your original functionality is going to change, that's when you might start overriding functions from your initial classes. That sort of makes sense. Does it sort of make sense? I hope so. Hang on. I was doing so well. So it's sound issues this week. This week, hello, welcome to Electronic Bash 25. Sound issues is the theme of our thing. Thank you very much. I wanted to introduce you to this idea, the UML diagram. The Universal Markup Language diagram, which is a visual way, a kind of antiquated visual way, not antiquated, a little bit passé, visual way of representing the relationship between classes and subclasses. So you can see here, sort of visually, our superclass, our main class is this person class, and every person in this bit of code has attributes called name, phone number, and email address, and a method called purchase parking pass. That's our main class, and then it has subclasses, student and teacher, with their own attributes, say student number and average mark. The teacher has a salary attribute, and then the student has methods is eligible to enroll, which probably returns a Boolean object, and get seminars taken, which maybe returns a list. So like I said, you don't see this that much anymore, but if you're building a more complex system of classes and subclasses, something like this you might see in documentation online, or you might find useful as a way of diagramming out sort of how things relate to each other. In any case, we're not going to use this anymore tonight. I just wanted to sort of throw this out there as a thing you might encounter in the wild. Let's go into our gameplay content demo. What are we saying over here? It's always worth the wait to see my... Thank you. Well, I'm glad you're getting... As always, as with all of the screw-ups, I'm glad you're getting something out of it, even if it is only my fireworks. So let's go to our gameplay programming example here. This is going to be... If you're following along online, this is the PyGame basic example, I think I called it there. Basically took the code that we wrote throughout the last session and pared it down to some of its essential. I took out some of the mouse functionality that we had built just to give us a really basic starting point to start playing with object-oriented code. So just to take 1 minute to walk through this existing code in case it's slipped your mind over the past couple weeks, we bring in a couple of libraries, most importantly PyGame, that's going to do a lot of our graphics interface work for us. And when we start using PyGame, we have to call this PyGame.init function. And like I said last time, that's just going to allow the library to figure out what operating system it's on, how does the monitor work, all that good stuff. We define our screen width and height, which we'll later use to build a screen. We load an image of our guy, our little jumpy guy, which hopefully I've put in the right folder, and a couple different sizes of him facing left and right. We define an initial position in X and Y, a speed and a vertical speed. We create a new screen object. This is how we create an actual window to display content on, is pygame.display.setMode. And, excuse me, we give it the size of our screen. And then we just loop forever while true. And true is always true, so while always, we loop. If we see the escape key, if we see the X button on our screen get pressed, we will exit. Fill the screen with black. We draw our guy to the screen at the X and Y location that the guy should be at. And then we respond to key presses to move left or right, or jump up or levitate in the air. And then we have a little bit of code to keep our guy on the screen. And then finally, our pygame.display.flip function is what tells the sort of backlog of changes to the screen to actually apply to the screen and show something. So if we run this, we should get, yes, our old friend. I think we called him Big Pip last time. There he is, hopping around, not super fast. Oh, and my other monitor just started working. That's weird. That's very weird. Well, who can say? So let's start to modify this. We'll use some of the treasure code that we've already written and make this code a little bit more object-oriented. So what I'm going to do, let's see. So go back to my treasure file here. I'm going to delete a little bit of this code. I'm going to incorporate this other file's worth of code into my PyGame code. So just so we have a different working file, I'm going to save this as PyGame with treasure. Treasure. And now, to bring that treasure file in its entirety into my code, I could do something like we've seen before. I could say from treasure import treasure. That should work, I think. Let's find out if that does. It may be a little grumpy with me. Oh, there we go. So now it's doing something interesting here. You'll see that I'm running this code, but I'm still getting my hello, my name is Ingot, and hello, I'm called coin. That's because of two things. One is when you do an import like this, you are literally telling Python to, when I get to this line, run all the code in this file and try and figure out where the treasure class exists within it. So if I have any statements like print statements in here, they're going to run. Though I deleted them in here, what didn't happen is I didn't save this file. You can see that the asterisk there, I have unsaved changes. And when you import a file, you're always using the last saved version. Now if I save this code and rerun my big pip file, we shouldn't see those print statements anymore. Yeah, there we go. Just hopping around there. So now I have this treasure class in my code. What do I want to do with it? Well, we might need to give this treasure class some ability to like have some parameters that relate to being drawn on a screen. So let's go back to our treasure class and make some modifications to it. So in addition to just a name and a value, I'm going to give it an image and a rect object, which remember is how we define X and Y locations. So I'll say self.image equals pygame.surface. Let's see, I'm gonna have to remember all the syntax for this, although I prepared one I baked earlier. Let's call it treasure for pygame. There we go. No. Pygame.sprite. Yeah, here we go. Boop. Boop. You saw nothing. So I would spare you going back and forth to the internet a little bit to look at the syntax again. I'm going to say that every treasure object has a parameter called image, and that's going to be a Pygame surface of dimensions 20 by 20. I'm going to fill it with a color. In this case, it's going to be like a nice like reddish yellow. So you'll see in this init function here, in addition to like defining some parameters, I'm also just running code, right? I'm just calling, surface.fill to fill up this surface with a particular color. You can do whatever you want inside these functions. It's just a matter of like how much is cramming too much into one function. Let me save that again. And I like to frequently run my code to make sure I haven't broken something here. So now I have that surface. And the other thing I wanted to do was, yes, here we go. And copy and paste this in, and I will explain it in a second here. So, you'll recall from last time the rect or rectangle object is the way that Pygame handles like physical size and location within a screen. And what we can do here is by using this image.getRect function, we basically get a rectangle that is the exact size of our surface, so a 20 by 20 rectangle. I want to put it at a specific location in the screen. So I'm going to say X location and Y location are going to be new parameters that I require when I create this treasure object. And then I'm going to move my rectangle by setting its X and Y parameters to those two values that I've fed into the constructor here. Right? So again, we haven't implemented this in our full program yet, but if I run that, if I run Pygame with treasure, yes, it should run just fine. But now let's add some treasure to it. So before we start our infinite loop, we're going to define some objects here. So let's say, my first treasure equals treasure, and I need how many parameters? I need name, X location, and Y location at a minimum, and possibly a value as well. So let's say my name is coin, my X location is 200, my Y location is 400, and we'll stick with the default value for now, right? So now I have this treasure object, but of course I'm going to need to actually draw it somewhere within my infinite loop. so that it's actually drawn to the screen. And we'll have to choose, so obviously the first step in our loop is we're filling the screen with black, so we should draw it on the screen after that, right? And then I'm drawing my guy in this step here. Let's say the coins want to be behind the guy, so we'll draw them first, and then if necessary, we'll draw the guy on top of them. So we'll say screen.blit, and then we need to give it a surface to draw, so that'll be my first treasure dot image. An image, you'll recall, is this surface object that we create. In fact, maybe surf is a better name for it. It's not quite an image. Yeah, let's call this the surf parameter. And you'll see changing, what that was called was just that simple. Self.surf, surf, surf. Easy, easy, easy. So I'll say blit, my first treasure dot surf, and then I have to give it what? An X and Y position? Oh yeah, so I'll say my first treasure .rect.x, my first treasure.rect.y. I think that's right. Let's see if that works. Oops, PyGame is not defined. That doesn't seem right. Electronic treasure.py line 5. Ah, I didn't actually import PyGame into my treasure class, so it doesn't know how to create a surface because it doesn't know anything about PyGame yet. Interestingly enough, so you notice it didn't throw that error until I actually tried to run some code that made a treasure object, because until then it was like, well, there's a treasure class here, but if he's not going to use it, I don't really care. I'm not going to try and run all this code. So what I want to do here is import PyGame so that my treasure object can make use of this pygame.surface function. Let's run this again. Oops, treasure object has no attribute surf. Well, that's not right. I just made an attribute surf. Let's see what's going on there. So in treasure here, S location, Y location. Okay. Yes, I missed something. Oh, was I changing this in the wrong file? Yeah, I think I was. Yeah, I changed this in my baked ahead of time cake is the problem here. I confused myself. I want self.surf will represent the surface that's associated with my treasure object here. Import PyGame. Yes, let's run that. Yeah, there we go. So now I have my little treasure object that exists at 200x and 400y, because remember from last time, x increases from left to right, y starts at 0 at the top of the screen and increases downward. Right? So now I have my first little coin treasure object here. Isn't that exciting? But it might be more fun if we had, I don't know, 10 of them. Let's see how we might do something like that. And this is now where using object-oriented code is really going to start to save us, because if we had just written some code in here to create one surface and give it a location and draw it manually to the screen, we'd be copying and pasting over and over again. But since we have this idea of a treasure class, we can reuse it for lots of things. So let's move that down here. And I will say for I in range 10. So again, we're doing this 10 times. We'll say my first treasure equals a coin, and we'll do object list dot append my first treasure. Right, so you'll see up here I'm creating an empty list just to hold the objects in my world. In my world. And now, as we go through this loop 10 times, we'll create a coin object, a treasure object, and we will append it to this list. Now, in a moment, we'll come back here and make it so that it's not always the same place. In fact, we could do that now. If this goes from 0 to 10, let's say that each of these coordinates increases by some multiple of the loop that we're going to. So this will sort of make a diagonal line across the screen here. So now we have a list of these 10 treasure objects. Let's draw them within our loop. So in our loop here, rather than just saying, where's our draw code? Yes, instead of just blitting our treasure to the screen here, what I will say is for, I don't know, obj in object list, is that what I called it? Object list, yeah. For obj in object list, remember that's our syntax for just stepping through every element of a list. I will say screen.blit, and then rather than referring to this as my first treasure, what I want to act on is the current object in the list that I'm referencing. So obj.surf, obj.rectx, obj.rect.y. So now when I run this code, now I have 10 coins, or 10 treasures floating around the screen. They don't do anything yet, but they could. So you can see, very quickly we're starting to reuse this code that we wrote for treasure to be able to create many objects very, very quickly that all share similar properties. To make things just a little bit more interesting, let's give ourselves a little bit of randomness to work with. Say from random import randint. Randint is a function that generates a random integer. So in our function here, rather than saying 50 times I and 20 times I will say x equals randint between, we don't want to go all the way to the edge of the screen, so let's say between 30 and screen width minus 30, and y equals randint between 30 and screen height minus 30. I think this is how I had spelled them in this bit of code. And then I will create my new coin at not a fixed position, but at position xy as determined by those random numbers. So now if I run that code, now our coins are showing up sort of randomly all over the screen. And if I run this again, we'll see they show up in different random locations, because that's what randomness means. Oop, there goes Pip. Bye, Pip. So now we have multiple objects. They're holding multiple bits of data. Let's run some functions on them. So let's say let's start with a very simple function. So let's say once a second, we're going to apply some interest to each of our coins. Not a very good game, but sort of the longer we can wait, the more valuable these coins will become. We'll also say once a second, we will print out the value of each coin to the screen, just to give ourselves a place to start. So let's see. Clock.tick, so we're doing 30 frames a second. So what I will say is, let's define a new variable called frame rate equals 30, and I will tick at a rate of frame rate. You remember this clock.tick function only allows our game, our window, to advance sort of at the maximum of this frame rate. So I'm saying clock.tick, I only want you to advance 30 frames a second at most. If you have to go slower for the sake of running code that you might be doing in the meantime, that's fine too. Let's see. I will need a variable to hold the elapsed time. So I will say total time equals 0. And then every time we tick, I will say total time plus equals dt. Right? So I'm going to total up all the time that has passed since we started running this leap. And I will say if total time is greater than, let's see, 1,000. So remember, so dt is going to be in milliseconds. So I'm going to count up by, an increments of 1,000. Why don't we just say total time equals total time minus 1,000, right? So this counter is going to sort of count up to 1 second and then reset itself. And print, what do we want to print here? Let's just start with a little test. We'll print 1 second every second. So now when I run this code, I should see once a second, I should see 1 second printing out down here, which it does. Now, it's going to become not obvious that it's still printing because, of course, it's just printing the same thing over and over again, but that's fine. So now we know that this function works. This, by the way, is something I often do when I'm developing new bits of code, is like, when I hit to a point, it's like, what exactly is this going to do here? Well, I'm getting ahead of myself. Let's make sure that the code that I've written so far actually does what I think it does. And I'll do that in the most basic way possible, usually by printing something to the terminal. Just like, hey, does this do something once a second code work? I think so. Just print something once a second. Oh, it does work. Great. Then I can move on from here. Right? So let's see how we can make this what we want to do here. So if we're greater than 1 second, then I'm going to reset my time counter, and I'm going to say for obj in object list, obj dot, what was it? Apply interest, I think is what we call it. Apply interest. Apply interest, and we'll say 5%. Right? And once a second, I'm also going to print the value of that object to the screen. And here's a little construction that might be useful to us. So if we print each object sort of, in its native form, we're going to have a list of 10 values showing up every time we do this. And I'd rather just sort of have one line of things. So what I'm going to do, rather than sort of having each print statement individually, is I'm going to say print obj.value, and then add this additional parameter to the print statement, which is this end parameter. Normally, so by default, the print statement adds a new line, basically hit the enter button at the end of whatever you type. By using this end syntax, I can say, rather than putting a new line there, put nothing and just carry on. Or let's, in this case, put a comma. just so we have a 10 separated comma values rather than a giant like list of print statements one after the other. And then when we're all done, just to break it up, I'm going to print nothing after it's all done, just to close things off and start a new line. So now, once a second, I should see a list of 10 values, incrementing by 5% each time. And much like before, we're going to the limits of precision here. Out in our various functions. So those coins are increasing by value every time. And just to make things a little bit more interesting, now that we have our randint function, why don't we randomize the value of the coins? I'll say randint between 1 and 20, let's say, is what these coins are worth in our fictional world. So now when I run this function, we'll see I have a list of 10 coins of various values, and it might be just a little bit hard to tell, but well, you can sort of see they're increasing by small amounts over the course of time. Let's see, what was the point of all this? What were we doing? Oh, we were going to, so the point of this was like how easy it is to work with lists of objects that all are sort of the same in value. What if a few of these objects are of our subclass iron bar type? What do we want to do with them? Well, so basically we're going to create a few objects that are iron bars, and the rest are going to be regular treasures. So let's start by that. Let's start by just creating a couple of iron bars. We'll say ingot1 equals iron bar. Do I need to provide it any parameters? I think I'm going to have to. Yes, iron bar takes what kind of parameters here? Nothing additional to treasure? Yeah, so we should be okay here. So we'll instantiate an iron bar the exact same way we did a treasure. We're going to say iron ingot x. I'll need to define x and y again. X, y, and its value is going to be quite a bit more. Let's say it's between 1,000 and 3,000. Let's say iron in our fictional world is quite valuable. And let's make a few of these as well. We'll say for I in range 3, right? We'll create an ingot object. We'll randomize its position on the screen. And we'll do object list.append my first treasure. Right? Not my first treasure. What do we call this? Ingot. Right, so now our list will have 10 treasure objects followed by 3 iron ingot objects. So now when iron bar is not defined, I didn't import iron bar. So for my treasure file, I need to import treasure and iron bar. So I have both of those classes brought into my code. So now we'll see we have a bunch of objects with low values and these various values up here that are, up in the thousands and are slowly increasing. And you know what we should do? Let's reuse our name of apply interest here. Rather than rusting, let's say that the apply interest function, in the case of an iron bar, represents the rust that's applying, right? Whereas the rest of the coins increase in value, the interest on an iron bar is essentially negative. So we'll say that its value is multiplied by 0.8 once a second. That's going to be its deprecation. Actually, let's do divided by. Let's do our divide by function. It's really rusting away fast in our world. Just to show how you can use sort of 2 different functions with the same name and how they apply. So let's run our code again, and you'll see, apply interest takes 1 argument, but 2 are given. It's that same typo again, right? So here's what's happening. So in the case of my treasure object, apply interest took this parameter interest rate, and in the case of iron bar, it did not. So I'm gonna have a hard time exactly overriding it here, but what I could do, interest rate, is give this an interest rate parameter and then just not use it for anything. That's a little bit of a hacky programming trick, but I think it'll do us fine for here. So we'll see again, we have some objects late in the list that have a huge value that's rapidly decreasing, and objects early in the list that are slowly accruing in value. Why don't we distinguish these just a little bit more visually by making the iron bars a different color than generic treasure? And here's how we would do that. So you'll notice down in our iron bar class here, we're just defining a couple of new functions, but we're not actually, we haven't created any new attributes or anything like that. What I'd like to do is when I create an iron bar object, I'd like to basically, do the same thing, make a treasure object, except in here, instead of filling my surface with this sort of nice yellowy color, I'd like to make it, let's say, a pale gray color, because iron. Sure. how am I going to do that without rewriting all of this code and then just changing this one little line? So like one way we could do it, right, is we could copy this entire function down into here and say, okay, for an iron bar, the init function is like the init function of a treasure, except that the color is different, right? And that would be fine. And if we run this, I believe this will work. This is another, untested before. Yeah, so there's our 3 iron bar objects popping up on the screen. They have a different color. So when we instantiate an iron bar object now instead of using the treasure init function, iron bar has its own more specific init functions, and that's what we're using. But, when as programmers, we try not to, retype code that's very similar. This is a recipe for things getting confused along the way, things not getting updated. Maybe we need to add an additional parameter. We'd like to sort of condense all this similar logic into one place. So how can we reuse the fact that we've already written all this logic up here and reuse as much of it as possible for our subclass iron bar? I'll show you. So first, let me get rid of all of this and introduce you to one more new concept in this class demonstration, which is the super function. The super function basically gets the superclass of whatever class you're working with. So in this case, iron bar's super method is going to give us basically the treasure class. So if I do a construction like super.init, and I give it my parameters here, which I'll just copy and paste. Right? So what this is saying is, hey, when you try and instantiate an iron bar object, well, there's now a special initialize function for the iron bar, but now just do exactly what you would have done for a normal treasure. Use treasure's init method, because treasure is the superclass of this iron bar class. Let's run that and just double check that I'm not lying to you. No, I don't seem to be, which is always nice. But now that we've sort of redefined, we've created our own initialization method here, I can also change whatever I want. So let's say, okay, so first initialize a treasure object, and then let's change ceph.surf.fill, and we'll fill it with a new color. Right? Oops, why did that not run? Oh, I'm running the wrong file. Now if we run this code, we can see now we have our 3 gray objects back again. And so we've reused a huge amount of our initialization code from our superclass here, using that super constructor. And then we made a few small changes that we wanted to make, like the color of the surface. Maybe it'd be the size of the surface. Maybe we want to have a different range of X and Y values. Lots of things we could possibly do here. But this sort of gets to the crux of why subclasses are useful, right? We reused all of this sort of setup code that we made for a more general case, and then we reused it using this super constructor and just changed a few little parameters about it to make a more specific object that might have new methods or options. Let me show you one more thing, I think. I've said that about 4 or 5 times. Let me show you one, just really this time, one more thing. Which is, let's say the iron bar object has methods that the treasure class does not, and we only want to run them on the iron bar object. So let's say let's bring back our rust function. We'll get rid of our apply interest function, so the iron bar will just use apply interest from treasure, and we'll bring back our rust function here. So within that rust function, I will say self.value equals self.value times 0.8. We always use 20% of our value every time something rusts, right? So what I'd like to be able to do here is I have my big list O objects, which has some treasure type objects which don't rust, and some iron bar objects which do. I'd like to run this this rust function only on the iron bar objects and not on the treasure ones. How would we do that within our loop? So, within our loop, once a second, we are using this apply interest function on every single object in that list. And that works just fine, right? We're applying interest to our iron bars and our generic coins. But if I wanted to rust just the iron bar objects, I can't just do, for every object rust, because the first time we try and rust a treasure object, it says treasure has no attribute rust. I don't know what you're talking about. One way I can get around this is to say, if obj.rust, obj.rust. So what's happening here? So let's see. This actually is saying if obj obj.rust not equals none obj.rust. So obj.rust, right? Obj is the current object we're looking at, and .rust is the name of the Rust function, which in Pythonic terms is really itself kind of an object. So we're basically saying if the Rust function exists for the object we're looking at, then do something. If the Rust object does not exist, if it is none, if it's not there, if there's no Rust function, Rust parameter, Rust object on this object, I don't want to do anything. But if we do have one, I want you to run that function. So now when I run our code, oop, treasure object has no attribute Rust. Why is that? Oh, did I not save the thing? Let's see here. If obj.rust not equals none obj.rust. Well, that should be right. Why is that not doing the thing? It's good. It's another learning opportunity. obj.rust not equals none obj.rust. Treasure object has no... I wonder if this construction will work differently. No, treasure object has no attribute Rust. Huh. I did test this before, I swear. If obj.rust not equals none. Well, this might be another opportunity to pull out the cake baked earlier for sure. Let's see here. Cake, PyGame with... Oh, that's the one I've been working on. PyGame with treasure. PyGame, treasure for PyGame, treasure class variables. I think I know what's happening here, but let's find out if I'm right. No, that's the same. If for object list, obj.apply interest 5, if obj.rust not equals none, treasure has no object. What am I doing wrong here? 10 points to Gryffindor for anyone who sees it. If obj.rust exists, obj.rust. Here, let's narrow down what's actually happening here. So we'll do nothing after our if statement. So we'll see, yeah, the problem is in the if statement itself. If obj.rust self.rust. Let's see, if true, obj.rust, this should also fail. Has no attribute, Rust. Yes, that is true. Iron bar, Rust, self. If obj.rust not equals none, obj.rust. I swear this is the syntax. Let's see. Well, if I'm wrong, we'll come back to it next time. It'll be great. If obj.rust... So here, I will show you can refer to functions in this sort of object-oriented way. So if I just say print obj.rust, right, the name of the function. Treasure, am I in the wrong line? No, I'm right. Wow, I am bewildered as to what's happening here, to be perfectly honest. Because this code runs just fine. Well, a little mystery for all of us here. Let me think about that as we move on to a couple other things. One thing that might be nice to add to our code, and I'll just glance over briefly, is collision detection. So when we run our code and Pip runs around and he like bumps into coins, it might be nice to have him actually like collect those coins. And as collision detection, I think I mentioned last time, is kind of one of the harder things to implement in video game design. Not that this is, a particularly thrilling video game, but detecting whether one thing is touching another can be just a little bit complicated. Thankfully, the PyGame library comes with some functionality for detecting collision. The way we would do that is making our objects probably subclasses of the sprite class, which is built into the PyGame library. And here I'll show you the PyGame documentation for that. Pygame.org. We'll go to documentation. Let's see, PyGame sprite. Up here. So the sprite class has a whole variety of methods for determining whether two sprite objects collide with each other are not based on their bounding rectangles. So this would be if you were going to implement collision detection, whether things were going to bump into each other, how I would do it is make my big pip and my treasure objects themselves subclasses of the existing class of sprite. And that's something that I feel like is worth mentioning. A lot of times you can get a lot of bonus functionality for free by subclassing your types to an existing powerful class from an extant library. If you have a library out there that does 95% of what you want to do, but you wish the class had another couple attributes or maybe saved its state in some way, just make a new class and say, hey, I'm a subclass of this other class, and here's my bonus attributes. Here's a couple more methods, and you're good to go. Could has attribute be used? Oh yeah, well, good. We'll get into it now. Yeah, Palmer, it's exactly what's happening. Is for some reason it's not finding that the treasure object has the method rust. What I'm not entirely understanding is here. Let's see. So yeah, so Nate, to your point, has attributes. Let's do let's do print obj dot header. I think that's right. If not, we'll print the dict. No, that's wrong. Print obj dot dunder dict, which I think returns all of the attributes and methods of that object. Yeah, So now we're printing out each of our objects in turn with its value, its surface, and its rectangle. Let's see. What I really want is the functions of that object. Coin, iron ingot, value, surface. If there's any error with rust, oh, maybe. Let's find out. Let's see. Define init, treasure, surface.fill, define rust. The indentation looks okay. Sometimes you can get into trouble here if your indentation types don't match in some compilers, like if you have spaces and then some tabs, but this one seems to be fine. Self.value equals self.value times 0.8. That seems fine. Let's simplify a little bit here. This will be a good way to close, is how, demonstrating a little bit of troubleshooting as we try and figure something out. So one thing I might do is eliminate, rather than doing 13 objects at once, let's boil this down to just one object. So I'm going to comment out most of my code here, and I'm going to create just one iron bar and no treasure objects. I'll say ingot equals an iron bar. I'm going to hard code it at a specific position, and I will append that to my object. So my object list should now just be this one object here. And I guess actually the point is I'm testing this code in this loop, so I'm not going to comment it out because I want to know if it works. So before we add the rust function back in, we'll just make sure, yeah, so I have one iron bar and it's slowly accruing interest over time. Great. So now if we do obj.rust, which should work because there's only one object in the list. Yeah, so now it's accruing interest and it's rusting every step. So the rust function on the iron ingot objects is working. But now let's manually add one coin back in. I'll say coin equals treasure. Coin, we'll also put it at a hard-coded position, and it has a value of 5, just to code that in, and I will also put that in the object list. In fact, let's put it after the ingot. .append coin. So now we have an ingot and a coin. Treasure object has no attribute rust, and that makes sense, right? Now we're sort of unconditionally rusting all the objects, which we can't do for a treasure object. That's the whole point. I'm going to say if obj.rust treasure object has no attribute rust. Nate, let's try has attribute. Has atter. I wonder if that's a method of the object itself. Yeah. Has attribute rust. Or is it object and then? There we go. Has attribute obj rust. Ah, there we go. Yeah, has attribute obj rust. So now we're printing out the value of each of the objects. The coin is increasing in value. The coin is second in our list here. So the iron bar is rusting, the coin is increasing in value. So has attribute, it does return the whether a particular object has a function or an attribute of a specific name, I'm just a little bit baffled by not being able to print this function definition. Let's write a little more code and see if I can, if we all can learn, and by we all I mean me, can learn exactly what's going on here. Let's just start a new fresh bit of code. I will say from treasure, and I'll just be lazy, I'll say from treasure import asterisk. So in contrast to this other bit of code where I said import these specific classes, import treasure and iron bar, in this case I was gonna say import everything. This is generally bad programming practice because you don't necessarily know all the classes that are in somebody's module. In this case I do. I'll just bring them all into my code here, and I will say, let's recreate our example. Ingot equals iron bar ingot. It's going to have an X and a Y position, but it doesn't need to know what those are. 200, 200, and 5. Let's see if this will run. This will be an object function test bit of code. Just make sure that runs. It may throw up. Yeah, there we go. All right, so print. Let's print out the ingot dot dict, which should give us all of the attributes of that object. Yes, it has a name, a value, a surface, and a rectangle, which is good. I print ingot.string. Let me print. Yes, so, okay, so here's interesting. So I mentioned earlier that this string method, the str method, is a built-in function, and we've actually overridden it in treasure here. And what I've done is say print ingot.string. And it's saying, okay, so ingot.string is a method of the treasure object here, and it's at this location in memory. It doesn't know much more else about it, but it's happy to print out that that is, yes, indeed, a function that we've stored in memory somewhere. So now if I print ingot.rust, yeah, bound method iron bar rust of treasure, and so on and so on. But now if I say print ingot dot feathers, just something it doesn't have, iron bar has no attribute feathers, right? Which is what I would expect. So now what I thought for... maybe I'm just wrong. I'd be happy to be wrong. Yeah, clearly it's throwing this exception before it gets a chance to compare, to do this comparison. I think I'm just doing this wrong. Well, that's all right. At least we learned something. So yeah, so one way you could do this is to use this has attribute function, as Nate thankfully Googled for us. Thank you, Nate. Nate, I'm embarrassed, frankly, a little bit, but I'm delighted that like the solution was like, let's see if Google has the answer. Let's see if Stack Overflow knows like how to check if object has function. And we found the answer, which is frankly, if I ran into this problem and couldn't solve it, that's exactly what I would do. So I'm kind of delighted that that's the problem-solving path that we ended up taking. So to come back to our original example here, we're basically now we're saying if all the objects in our list, and let's, we'll go back and take out this manual business, and we'll go back to uncommon out, so we have a lot of coins and a lot of iron bars. Now the coins are increasing in value, and only the iron bars are rusting because only they have that attribute, only they have that method rust. So that's one way that you can... you know what we could do to solve this as well? Palmer says, wondering if it isn't seeing the rust in the treasure class. You're referring to the treasure class at any point instead of the treasure.iron class. So it's definitely not seeing the rust function in the treasure class, and that's why it's throwing the error. I have a thought. Let me just remember if this is the syntax that I'm thinking of. Yeah, rust doesn't technically exist. Rust doesn't exist in treasure at all. But let me see if this syntax works. If obj rust obj.rust, this might not be right too. Not subscriptical. That's all right. I tried. Yeah. Well, if I think of better syntax for this, I'll feature it in our episode in a couple of weeks. Our spooky episode. Spoilers. We'll get to that in just a little bit. So this is one way of managing objects, objects that are, types and subtypes that may be doing different things. You could also maintain a list of all of your, say, rustable objects and only call the rust function on them. That would be sort of the organizational way to organize this, rather than sort of testing with every object if it can do a thing and then doing it. You could maintain your sort of lists of objects separately. Yeah, so Palmer, what is definitely happening is it is going through this list of objects, it's finding some treasures, it's trying to call the rust value on them, and it's not finding that value. Now, one way I could solve that is say self.rust equals none, and sort of manually defining that this parameter is nothing. But I don't really want to do that, because then my programming pattern depends on, for every time I make a new subclass, copper bars and diamonds and jewels, or maybe jewels first, and then like diamonds and rubies and emeralds are subclasses of that. And they need to be subclasses because they all have different magical powers in this world. I don't know, we're getting ahead of ourselves here. But then I would have to come back and sort of define all of the various parameters I might want to test as none in the base treasure class, and that's kind of messy. I guess I'm wrong. I thought there was a cleaner syntax than this, but I will circle back on that next week, in 2 weeks from now, I suspect. So I know we have not gotten super deep into the broader topics of object-oriented code and how you might choose to organize your code to take advantage of some of the code reuse that object-orientedness gives you. But I hope this is like a very, the fundamentals of how you write your own class with its own attributes and methods, and how you subclass a class, which I know I stumbled on a little bit here. But the subclassing is a super powerful way to reuse the functionality you've already written, and make more specific objects out of more generic ones. I should also say, in case I haven't, there's no reason you have to have just one superclass and one subclass. You can imagine a situation where, in the context of our big pip game, we might, in many games you have a context of just like an entity, which represents a physical object, which has maybe just like an X and a Y coordinate and a thing you can draw to the screen. And then a subclass of that might be monster. And monster is a subclass of object, so it has an X and a Y coordinate and an image, and maybe it needs like an artificial intelligence component, right? So it has maybe an act method that causes it to do things, right? So that's a monster. And then you might have subclasses of monster like dragon and humanoid and various things. And humanoids can hold things, so they have an inventory object, and dragons can breathe fire, so they have a breathe fire method. And then within dragons you have a so you can go as sort of as many levels deep as you need to clarify what's going on. And the example I pulled for sort of demonstrating this is actually the GPIO0 library itself. We referenced the LED object earlier. So let's go into, let me pull, I guess I did not pull, but I shall now. I'll pull up the GPIO0 code that is hosted on GitHub here. We'll go into GPIO0 output devices, and I'll show you the code that exists for that LED object we were using back at the beginning, because now we have a little bit more tools to understand it, right? We can see we're defining a class. I'll zoom in a little more. Boop. We're defining a class called an LED, which extends this other class called digital output device. So we'll want to look at that in a second here. We have some very nice comments about how the LED class actually works and what example code you might with. Very well documented library. I'm very pleased. We come down to the actual code, and the actual code that's within the LED class just says led.isLit equals led.isActive. So it has a state, a variable called isLit, and that's equivalent to the active state of that LED. And that's all of the code in the LED class, because we're right on to defining a buzzer right after that, which gives us the hint that most of the relevant code is actually going to be defined in its parent class, the digital output device class. So let's go look at that. We'll go find digital output, and we'll find up here. Here we go, class digital output device, which is itself a subclass of an output device. It represents a generic output device with typical on-off behavior. Extends output device. So we have some init method, which is also referring to the superclass, its digital output device. It has a few specific methods like getting its value close or open, off. Those are specific to a digital output device, has on and off methods. But we can see we're also the subclass of an output device. So if we go up to output device, we can see that represents the most generic form of a thing that can create some output. And even then, it is a subclass of a general GPIO device, input or output, and a subclass of a source mixin. We won't talk too much about multiple class subclassing, just know you can actually inherit properties from multiple parent classes if you want to. And again, it's creating some parameters of its own, using this super directive to create sort of the parent object, and then doing some modifications to it. It might have an on state, an off state, and so on. So this ability to create a more general parent class that encapsulates high-level behavior and then create subclasses with more and more specific functionality is super powerful. It allows you to be like, an LED is one line of code tacked onto a generic output device. A buzzer is 2 lines of code, slightly different code, that are also an output device, and so on. So like I say, we're just scratching the surface of what object-oriented programming is and can do. I mostly wanted to expose you to the syntax and the process of creating your own classes, understanding what classes are. So as you're playing around in Python libraries or libraries in your language of choice, you can sort of understand what you're looking at and start creating your own classes on your own. I highly recommend, especially for this lesson, which I know is a fairly abstract one, that you go and write some code and play around with creating classes, because if any of this is a little bit unclear, and clearly there are things that are unclear to me as well, working through those problems, working through those questions is the easiest way to gain that understanding. That is all the lesson I have for you this week. It's like an hour. It's before 2 hours done. It's pretty wild. I do want to preview a little bit of what we're going to be doing in 2 weeks' time, which will be October the 25th, I think, if my math is correct, which will be coming right up on Halloween. And so we're going to do a little bit of a spooky time here. What I really mean is we have spent the past few sessions really focusing on like the digital and programming side of things, and I think that's great, because that's partly why I wanted to pivot to Raspberry Pi and Python, is there's a lot of cool programming topics to talk about. But I do a little bit miss the physical interactivity component of this, which is what was such a joy about the Arduino series of classes, and partly what's really cool about the Raspberry Pi is, as we've seen, it makes it a lot easier to do physical interactivity projects with a computer. So in honor of Halloween and in honor of doing some more physical interactivity, I think for the 25th, we're going to do a sort of synthesis of a lot of the skills we've drawn together, from programming in Python, object-oriented programming, controlling output devices, to build the idea in my head now, and it may get revised and I'm open to suggestions, is to create like a spooky Halloween prop. And what's in my head is like a spooky jack-o'-lantern. Maybe not a real pumpkin. It might be a 3D printed pumpkin just for the sake of like workbench cleanliness around here. But in my imagination, maybe it has a couple of servos that move some eyebrows. Maybe it has some lights inside of it that glow on and off. It plays some sound, so we'll look at playing sound files through Raspberry Pi. Maybe it says spooky things. Maybe we'll get a motion or a fire sensor in there. Ooh, we haven't done fire sensors in a couple months. That'd be fun. And maybe just to wrap in the Internet Week, maybe, I don't know, maybe the easy version would be like to ask the internet when like sundown is and automatically turn on. The like creepier version would be like pull down like facts from the internet, or like maybe the current weather, and adjust its behavior based on that. Like it's a dark and stormy night, or it's a sunny day, look out for invisible vampires. I don't know, we'll figure out something fun. But I want to wrap all these things together and build like a cohesive sort of program out of these different functionalities we've been playing with over the past few weeks. And I think the Halloween themed idea will be a way to do it. I don't swear it'll be a pumpkin. Maybe it'll be a ghost or a witch or a wizard or a zombie or something like that. But I think that'll be a fun way to sort of wrap some of these skills together. It also, I want to involve some of the skills that would be, or some of these, abilities that we now have that are specific demonstrators of things that are easier to do on a Raspberry Pi than an Arduino. Right? If all we want to do is make a couple servos move the eyebrows, that would honestly be easy on an Arduino, right? To move some servos around, flash some lights, totally easy. Asking the internet for information, though, or playing sound files or things like that, are things that are better suited to a sort of a more computing, like a more desktop computer-like environment. And so those are things I definitely want to build in. Whether we go the extra mile and like build in a little display, or something like that. We'll see. We'll see how much time I have over the next couple of weeks. We just opened a new exhibit at the museum I work at, and we're closing one this week. So we'll see how in-depth we get before the 25th. But no promises whether I'll be in costume for the 25th, but I hope so. I think that's all I got for you this evening. Thank you so much for being with me here on another Sunday night. I really do find it delightful. Thank you for bearing with some of the technical hiccups and also the coding hiccups. Nate, I'm gonna go find the answer to what I was thinking of as that construct. I know there is an if construct that allows me to do this thing, and of course here on this Sunday night with a very strong pigeon porter, I just can't think of what it was. But thank you, Chris. You're being mean. No, it's fair. Yeah. Well, what's all the closing business? As always, I hope you're being well. I hope you are staying safe, washing your hands, hydrating. I hope you're using this as a place to draw strength from and like encouragement for the week and going out and doing good things in the world. I hope you're all registered to vote and you have a voting plan. That's super important these days. And I hope you are taking good care of all the people out there who need it, because it's really a privilege to be here with you on the Sunday nights. It brings me such joy. The triumphs and the struggles in equal measure are a lot of fun. So thank you again, and I will see you in 2 weeks. Good night, y'all.